Hello and welcome to a hypothesis test for population proportion example. So in this example, a study was run to determine if more than 65% of California community college students work while in school. A random sample of 200 students was found to have 142 who work. Is there enough evidence at the 5% significance level to conclude that more than 65% of California community college students work while in school? So the first thing we need to do is simply understand the problem. So I'm going to first just look for kind of what our research question is. So our research question, we're essentially asking if more than 65% of California community college students work while in school. And then we have this again asked once more. So that first sentence and this last sentence are both essentially our research question. So this is our research question. Before we get into our sample information, let's just verify that we are dealing with proportion and a hypothesis test, as this video indicated. So we have is there enough evidence? We're asking if to verify a claim. So this is a yes/no question. Which means it is a test, a hypothesis test. Then we're looking at if students work while in school, and we're looking at percentage. So we're looking at the variable is if they work while in school. That's a categorical variable. And so we immediately know we're dealing with proportion if we look at that way. Or we can just see that we're looking at more than 65%. We're dealing with percentage, or we're dealing with proportion. So we're looking at, is there enough evidence at the 5% significance level to conclude this? We're talking about a proportion test. So we are looking at a hypothesis test. For population proportion. If we look at our sample information, so let's find a color I have not yet used. So the random sample of 200 students was found to have 142 who work. That is all talking about our sample. So our sample, we have it's random. We had a sample size of 200, and we had 142 yeses. So in other words, our sample proportion, we would do 142 yeses out of 200 responses, and we get 0.71, if I did that correctly. And then our research question indicates that we are asking, is the population proportion P greater than 65%? Or in other words, is P greater than 0.65 is what we're asking. And then we have our significance level of 0.05 or 5%. So from here, we want to state our hypotheses. I'm going to write them in both words and symbols. So the trick here is essentially to look at your research question. As long as your research question has a lean to it or a not equals to in it, then the research question will give us our alternative hypothesis. So we're asking if more than 65% of California community college students work while in school. So the alternative hypothesis will just convert that into a statement. So for our hypotheses, we will have our null hypothesis and our alternative hypothesis. The alternative hypothesis should just come from the research question. And it should have with less than, greater than, or not equals. So our alternative hypothesis would be just the research question in sentence form. So more than 65% of California community college students more than 65% of California community college students work while in school. Once we have the alternative hypothesis, we can get the null hypothesis simply by converting that statement to equality. So to go from alternative to the null hypothesis, then we'll just convert our HA to equals. So instead of more than 65%, we'll just do a flat 65%. We have 65% of California community college students work while in school. And then if we take these and put these in symbols, this is equivalent, our null hypothesis is equivalent to saying the population proportion P is equal to 0.65. An alternative hypothesis is equivalent to saying our population proportion P is greater than 0.65. If you struggle with your inequality symbols, we are looking greater than 0.65 means we're looking 0.65 or to the right. And so we want to use the symbol that points to the right. All right, so next up, we have to justify that the study was well run and that we can run the test. So we have two things that we need to check. We need to check that it's a good sampling technique. And in order to have a good sampling technique, we need to have that it's random and drawn from the whole population, or drawn from the entire population. So I apologize for the scrolling, but we do indeed have our random sample from our students. So we're going to assume then that that's true. So going back down, we're going to go ahead and we have random. The wording, we're going to assume it was drawn from the entire population. So we have a good sampling technique. Then we also need to check that we have the normality conditions. And the normality conditions when we're, this is in this case of the p-hat distribution, since we're dealing with proportion and sample proportions. Now the normality condition here is we need n times p and n times 1 minus p both to be greater than or equal to 10. Right? So we need both of these 10 or more. So just a heads up here, difference between hypothesis tests and confidence intervals. We have an assumed p in our null hypothesis. So we should use the null hypothesis p equals 0.65 in place of p. For confidence intervals, we don't have assumed p, we just have whatever we got from our sample. And so that's why we approximate the p-hat. But for hypothesis tests, we do have a known p. And so what we'll have then is we have that n times p is equal to 200 times 0.65, otherwise known as 130. And n times 1 minus p is equal to 200 times 1 minus 0.65, otherwise known as 70. Both of these are indeed 10 or more. And so we have our condition met. And so we can simply say that we can run the test because a good sampling technique was used. And the normality conditions were met. All right, so next up, we have to understand the sampling distribution. So the sampling distribution that we are talking about here is the p-hat distribution. And we need to know shape, center, and spread. So for our shape, we saw in step 3 that it was normal. The conditions were met. For center, for the p-hat distribution, we know that the mean, or mu sub p-hat, is simply equal to p. Again, this p is going to be from our null hypothesis. And so our mean will be that mu sub p-hat is equal to 0.65. Then for our spread, our standard deviation, or sigma sub p-hat, is equal to the square root of p times 1 minus p divided by n. Again, the p that we are working with is going to be from the null hypothesis. So we have the p is 0.65, and we are told n is equal to 200. So we have our sigma sub p-hat is equal to the square root of 0.65 times 1 minus 0.65, all divided by 200. Now I'm going to go over, switch over to decimals, which you are welcome to use. And you can make it so the formula looks precisely like this over in Desmos. So if we type in our formula, we have the square root of 0.65, and then we have parentheses 1 minus 0.65, and then we were dividing by 200. So you can see here, if I can enlarge this a little. I apologize. Now it's out of shot. Let me readjust. So as you can see here, I've made this left side look precisely like what I had written out. And so the advantage of using Desmos as opposed to a scientific calculator is that you can make it look exactly like what you have written and verify that you've typed in the correct thing. So we wind up getting 0.0337 as our standard deviation. So now let's switch back to our notes. We had, this was equal to 0.0337 approximately. We technically kept going. So we have our shape, center, and spread. The next thing to do is to find the probability of getting a sample as extreme as ours. That as extreme as is going to depend on our hypothesis. So this depends on the alternative hypothesis. And so since our alternative hypothesis was P is greater than 0.6, oops, that's not a 6. P is greater than 0.65. Since we have greater than, that means that we're looking at things more greater than our sample. So this means that we're looking at, so as extreme as our sample means greater than our p hat. So this as extreme as changes definitions depending on your alternative hypothesis. If the alternative hypothesis was less than, then as extreme as our sample would mean less than our p hat. And then we're supposed to figure out if our sample was surprising. So let's just draw a picture and see what we're looking at. So here we have our center was at 0.65. So we have a mean of 0.65 and a standard deviation of 0.0337. And then our sample was at, we had p hat was 0.71. So our sample is going to be somewhere over here, 0.71. It was our p hat or our sample. And then as we just indicated, we should shade to the right. So we're looking to the right. Again, this is the p hat distribution we are considering. So we have our center, we have our standard deviation. We can go ahead and convert this to z-score. So if we convert to z, the only thing we need to convert is that 0.71 that is of interest. So we have a p hat equaling 0.71 is going to be our data. So we have z is equal to our data value minus the mean divided by the standard deviation, or z is equal to 0.71 minus 0.65 divided by, I'm just going to use 0.0337. And once again, if we switch over to decimals, we can do this calculation. So we had in parentheses, next box, we had in parentheses 0.71 minus 0.65 and the parentheses, and then divide by 0.0337 approximately. So I get 1.78. If you did more decimal places, you might get a value slightly different. Right? So if we kept going to 6, 8, 4, etc., it would still round to 1.78. So we have about 1.78 for our z-score. Let's go ahead and switch back to our notes. So we have z equals 1.78 approximately. So our new distribution we're looking at the z-score. 0 is always in the middle. And we are now concerned with 1.78 as our z-score. And then we're looking to the right. So from here, we use our normal distribution calculator. Which we have over in Canvas, and we are interested in 1.78 looking to the right. So again, I'm going to switch over to the normal distribution calculator. I apologize, I am unable to zoom in on this video or on the screen. So we have 1.78. We'll hit enter. And then we're interested in the right area. So I'm going to take a picture of this and add it to our notes, and then I can zoom in. So again, we were interested in the area to the right of 1.78. So we are interested in the value 0.0375. So we get a probability or our p-value is equal to 0.0375. So essentially what this means is that if the null hypothesis were true, so if it is true that 65% of California community college students work while in school. So if this assumption is true, then there is a 3.75% chance that a random sample of size 200 California community college students would have more than our sample proportion, so more than 71% have work while in school. So this is our interpretation of the p-value. I'm going to give myself a little more room here. I apologize. I'll just ignore the rest of the stats. All right, so we have this statement here. So a 3.75% chance of getting a sample like ours or more extreme is a pretty slim chance. So we put 5% as our cutoff for surprising. So note our significance level equals 5% is our cutoff for surprising. Right. And so 3.75% is more rare than 5%, which was our cutoff. And so what we have is that our sample would be surprising if the null hypothesis were true. So our sample would be surprising if the null hypothesis were true. So this lends itself towards concluding that the null hypothesis may not be true, right? If our sample is surprising, that leads us to doubt the null hypothesis. So we're going to doubt that null hypothesis. So when we draw our conclusions, we have kind of our two possible conclusions. So either there is enough evidence to conclude HA or there is not enough evidence. In this case, because our sample was so surprising, we do have enough evidence. So our final conclusion would be there is enough evidence at the 5% significance level to conclude our alternative hypothesis. So to conclude that more than 65% of California community college students more than 65% of California community college students work while in school. So that is our hypothesis test for population proportion.